parameter theta, which I only care about is quantum estimation. I'm not gonna calculate the posterior distribution, but given theta, I'll sample the little random variable z, and given z, I'm gonna sample the observed random variable x, right? So I want to find out the optimal hyperparameters theta. Right? At the same time, I want to compute the posterior distribution of the little random variable z, given x, and given this optimal parameter theta, right? So the core idea of the EM algorithm is the decomposition of the mod evidence, right? So in mod evidence, you record is sometimes it's called log evidence, but which is log marginal probability of the observation x given theta, right? So we can use Jensen's inequality to derive that this mod evidence is essentially a summation of a lower bound. It's called evidence lower bound, which is an expectation. An expectation under any non-trivial distribution over the later random variable z. So non-trivial means that I need to ensure that this Q of z is non-zero in the whole sample space. The expectation of the fraction, so the numerator is the joint probability. Denominator is the this extra distribution Q of z. Plus a KL divergence between your introduced distribution over z and your true posterior of z given x and given theta. So this is a very important decomposition because the KL divergence is always non-negative, right? Remember, KL divergence represents kind of a difference between one distribution and another distribution. They're always non-negative, and when it arrives at zero, if and only if these two distributions are exactly the same, right? So the first term, which is essentially an expectation of this log fraction, under Q of z is called mod evidence lower bound because it's smaller than or equal to this mod evidence. So EM algorithm essentially optimize or maximize the original mod evidence, but never calculate this original mod evidence. So it essentially uses this evidence lower bound as a kind of a bridge or surrogate to do this. So the idea is that we treat this evidence lower bound as a function of the model parameters theta and this actual distribution Q of z. This actually can be considered as a function of two parameters. The first parameter is the model parameters, the hyperparameters in our original probabilistic model. The second is some kind of free distribution Q of z. And we know that when we choose Q of z equals to the exact posterior, the true posterior, Q of z given x and given theta, your bound is equal to the original mod evidence, right? Because the KL divergence will then become zero. The bound reaches the mod evidence. So the idea is here. So at whatever, like at any choice of theta, I'm going to first choose Q theta to be the true posterior of z given x and given current theta. Right? So we denote this particular choice of Q of z by Q star z. So at this particular choice of Q of z, we have the lower bound equals to the mod evidence, right? And now I'm gonna fix this. I'm fixing Q of Z to be this Q star Z, and then I optimize this lower bound with respect to theta only. So obviously, after maximization, I'm gonna increase the lower bound, right? So suppose I find some maximum value of this lower bound, the corresponding optimal theta will be denoted as theta nu. This is my current lower bound, right? And now, if I want to, now we know that because Q star Z is just a true posterior distribution under the old version of theta. So this is still upper bounded by the mod evidence of X given theta nu, right? Why? Because currently you have to make the true bound, the lower bound to reach the true posterior, if and only if you choose QZ to be the current true posterior. See that here, right? Otherwise, you're always less than with mod evidence. So now we can see by only optimizing the evidence lower bound, I'm gonna increase. I have increased the true mod evidence. That's the key idea of the diagram. So the first step, we calculate the true posterior of the current model. Given the current model parameters, we call this as an E step. And then we fix the Q of Z and maximize the lower bound with respect to the model parameters. We call it M step. So one E step and one M step consists of one particular iteration. And one particular iteration will ensure the increase of the original mod evidence. So we continue to do that until convergence or the maximum number of iterations is achieved. That is, yeah. So any questions so far? Because this is very, very important. Our variational inference framework are based on same decomposition. So if you have any question clear, ask now.
About the naming, say the px given theta. If the theta is not numerical but just parameter, so this one is simply likelihood, not mod evidence.
Yeah, it's a likelihood, or this is the likelihood, but you do not consider Z, the value of Z, because it is unobserved. Like basically, you can consider like two types of likelihood, right? First likelihood that you consider arbitrary value of Z, say you can compute the log probability of Px and Z given theta, right? So you can compute the likelihood. But what if I want to integrate of Z? I just compute the likelihood of the observed data. This is called mod evidence. Why it's called mod evidence? Because I'm gonna remove everything I have never observed. I just calculate the likelihood of my observation.
So in this way, the model evidence and the likelihood of the data, they are just the same thing.
You should consider it in this way. Mod evidence is a kind of likelihood.
Okay.
The likelihood
of the data, right?
What?
The likelihood of the data given the model.
The likelihood of the pure observations.
Pure observation.
Yeah. Like you can because we have like a hierarchical model, right? You have observed variables. You have unobserved variables. Like I can plug in any values for the unobserved variables. I want to say, okay, what is the likelihood for this? But this is not mod evidence. The evidence has to include all possible setting of the linear random variables. We integrate them together. That's why we call normalization. Then we form this mod evidence. Otherwise, your evidence is not complete. Any other question?
Is there any case when we would set Q of Z to something other than the probability of Z given X of theta?
Yeah, that's a good question. So actually, we'll see that if you can really calculate, the true posterior every step, or it's like you win the lottery. This is very hard. So that's why we'll seek for like different approximate form of Q of Z. So for Gaussian mixture model, it's simply a special model that you can accurately calculate posterior distribution at every step. But in many other cases, or 99% of cases, you won't be able to calculate this. Any question? Okay, great. So now let's look at the global variation inference framework. So I will still consider a general model, and we'll derive the some general framework for the global variation inference. Then we look at some particular example and look at detailed updates to experience how we conduct this variation inference. So again, we assume this simple general model. So we have this hyperparameter data, which we do not care about distribution, so we consider it as some points. And given data, we sample the data random variable Z. And given Z, we sample the observed variables X. So both Z and X are considered as random variables, and we care about their distributions. Right? So again, if I want to compute all the evidence, the marginal distribution of the observed random variables X or A, given particular data, I have to integrate out the latent random variables in the joint probability, right? So as for now, I just assume data is known and fixed. So if you don't like it, you can assume I move theta into Z, and then I assign some uninformative prior on that. So basically, we do not care about theta right now. And later we'll consider how do we draw an estimate data and approximate posterior distribution of Z. So, but as for now, we first fix theta. We assume theta is known and constant. And then the question is how to compute the posterior distribution of Z given X, because theta is assumed to be constant. I just remove it. So according to base rule, the posterior distribution of Z given X is the joint probability of X and Z divided by this marginal probability of X, right? In which we have to integrate all Z in this joint distribution. And as we emphasized at the very beginning, in most of practical cases, you won't be able to do this integration, especially when P of X and Z are complicated and Z is high dimensional, it's really infeasible, right? So the example I have seen so far, like Gaussian mixture model, Bayesian linear regression, are just a few exceptions. And also, such exceptions include the conjugate prior, right? So if the prior of Z is conjugate to the likelihood of X and given Z, right? So here, if prior of Z given theta is conjugate to this likelihood of P of X given Z, well, you don't need to do this. But in most cases, you either have to sacrifice your expressiveness of your model. Right? You have to simplify the model. You have to make oversimplified assumption to allow the computational tractability, or you have to address this computational difficulties if you do not use conjugate or something like that. So in most cases, you cannot get analytical results. So here's one example we mentioned before. Right? So suppose your prior of Z is a Gaussian, simply Gaussian, but your likelihood, namely the probability of X given Z, is Bernoulli likelihood and parameterized by a sigmoid function of Z. You won't be able to compute this marginal distribution. You won't be able to compute the posterior distribution analytically. Right? So then how can we? Then we'll have to like find another way, right? Now that we cannot compute exact posterior, we're looking for some approximate posterior. Right? We want to find some approximation, just like Laplace approximation. I got to now that I'm not able to compute the exact posterior distribution, I'm going to use like some Gaussian distribution to approximate, right? So Bayesian inference actually has the same goal, right? I want to find out approximation distribution, right? That in some sense best approximate the true posterior distribution. Right? So the key idea is colored as blue part. So I'm going to read it. So now that the true posterior is complicated and tricky to compute, can we find a simple form of the distribution? For example, Gaussian. But it's not necessarily the Gaussian. Right? You can use mixture of Gaussian. You can use T distribution. You can use whatever you want. Right? And that can approximate the true posterior. In other words, can we designate a family of simple distributions from which we find the best member that is closest to the true posterior? So that's the key idea of the variational variational inference. So suppose this is our true posterior. We already know that we cannot compute that, right? So now our compromise is that I'm going to designate a family of easy distributions like this, right? And then I will search over this entire family of distributions and find one that is closest to the ground truth. That's it. That's the variational inference idea. So this strategy actually requires you to first define what kind of approximation family you want to use, right? So obviously, you can intuitively you can take this kind of trade-off. Right? If I have a designated very small family, right? Very small family, then computationally it can be like much cheaper. But you can imagine that the best approximation will still be quite bad. And when you enlarge the size of approximation family, you are likely to find a better approximate distribution, right? At the same time, searching over the larger family of approximation distributions will be more challenging, right? More computational costly. So this is kind of a trade-off. And if you do not restrict the family of distribution you want to approximate, right? Your distributions cover all possible distributions, then you are doing the exact inference, right? But really it's entrapment. So that's why it's called variational inference, because you have the rights, you have the flexibility to designate the family of distributions you want to search. And theoretically speaking, like you can always enlarge your family of distributions to be big enough to include the true posterior. Then theoretically speaking, ideally you can find out the true posterior, right? But practically that won't be feasible. You have to shrink the family of distributions and find out someone to allow a feasible computation. So going back to our example just mentioned, suppose your prior of Z is Gaussian, and your likelihood is Bernoulli likelihood parameterized by a sigmoid, right? We know that this posterior is infeasible to compute. So now I can designate some approximation family, right? Say a Gaussian, right? And then the question becomes like, how are you gonna identify the optimal parameters for this Gaussian, right? Mu and sigma. How can we do that? Right? In the Laplace approximation, well, we do not explicitly optimize these parameters. We simply set mu to be the map estimation, right? And we set sigma squared to be the inverse of the negative Hessian, right? But in the variational inference framework, you're gonna use an explicit searching procedure. You're gonna optimizing mu and sigma according to some metric. Right? So now let us look at how we optimize those parameters for the approximate distribution, right? So obviously, to optimize something, we need to come up with some objective. So we need to some metric that measure how far are we from the true posterior to the approximate posterior, right? And then we're just optimizing some this measurement to find out the one which is closest to the true posterior, right? So one such measure is the KL divergence, right? So again, we use KL divergence. So KL divergence is really central in the approximation inference family. That's why we discussed it at the very beginning of this class. So naturally, we can, by designating the family of approximate posteriors, say a Gaussian, or mixture of Gaussian, or t-distribution, whatever, right? So to identify the best parameters of the approximate posterior, I can minimize the KL divergence between the approximate posterior and the true posterior, right? So intuitively, this is rational, right? So I want to find out some distribution which is closest to the true posterior, and to measure the distance or measure the closeness, I use KL divergence. Although KL divergence is not rigorous distance metric, right? But here comes a problem. Right? What is the issue?
We don't know the posterior.
Yeah, we don't know posterior, right? It's something like, if I can do this, right, that means I can calculate the posterior distribution exactly, right? If I can calculate exact posterior, why should I approximate, right? So obviously, this is kind of something like experiments of thinking in mind, right? We will never be able to execute in practice, right? Obviously, people will think you're a psycho, right? So the issue is that actually we cannot do this. That being said, we need to find an alternative way to do this. An alternative way that we never need to evaluate the true posterior. How can we get detour of this? This leads to the form, leads to the decomposition of model evidence we derived before. Right? So remember, using Jensen equality, we have derived that the model evidence is the summation of the lower bound, which for now we call it the variational lower bound, plus the KL divergence. So now we assume like hyperparameters are fixed. So so this model evidence is a constant. So this constant consists of two terms. One term is the lower bound, one term is the KL divergence. If we consider this Q of Z as your approximate posterior distribution, if you maximize this lower bound, it is equivalent to minimize the KL divergence. So visually, you can look at this. Our evidence is fixed. It's just this, right? It is a summation of this lower bound plus this KL divergence, right? So if you are trying to maximize your lower bound, you actually squeeze the KL divergence, right? So instead of like directly minimizing this, which is invisible, we maximize the variational lower bound. That's the key idea. And if you take a look at this calculation of variational lower bound, we found that we never need to compute the true posterior, right? All we need to do is to evaluate the joint probability distribution. The joint probability is always assumed to be able to compute, right? When you design the model, you can write down joint probability and compute it. The true barrier is that how we do the normalization to obtain the true posterior, right? But it's never like hard to compute the joint probability. So this is the key idea of diversion. We maximize the variational lower bound, which is equivalent to minimizing KL divergence. So, so what I previously I called this is the model evidence lower bound, right? So now I add one fancy word called variational lower bound. Why? The reason comes from the meaning of variational. Variational usually means that I do some transformation of some function or whatever objective function, right? So by this transformation will give you introduce actual parameters. In our case, we introduce this actual distribution Q of Z. If we do not put any constraints of Q of Z, then you're maximizing this lower bound. You're still, conceptually, you can still recover the evidence. Why? Because if you set Q to be the true posterior, it is equal to the evidence, right? But in practice, I have to restrict the family of Q. I have to restrict the family of Q such that this computation is feasible, and in a acceptable cost, I can find out a good approximation. So this is the sum equation. So conceptually, if you do not restrict the family of Q, just like the figure I draw here, right? If I do not restrict the family of Q, like it is big enough to include everything, then conceptually I can still find out the true posterior, right? But in practice, I have to heavily restrict the family of this distribution Q to gain the computational benefit and to find out some approximation. That's called variational. That is why it's called variational one. Any ideas so far? Any questions so far? Okay. So now here comes our global variational inference scheme. So first we need to design a family S of the approximate posterior Q of Z. And then we find out our optimal approximate posterior by maximizing this variational Probabilistic lower bound, which is expectation of this log fraction under the approximate posterior Q of Z. So this fraction is dividing the joint probability of X and Z by Q of Z. So usually there's a trade-off. The larger the family S, the better approximation quality, but the harder the optimization. So in practice, you can choose whatever family you want. But here I'll give you, I'll introduce a commonly used approximation family. It's called mean field variational family, and the corresponding inference is called mean field variational inference. So the mean field variational inference assumes the approximate posterior is factorized. So basically, you have this vector of the latent random variables, right? So just partition them into different subvectors, say z1, z2, blah blah blah, zn. Then I assume my approximate posterior has this factorized form. So namely Q of z1 times Q of z2 until Q of zn. So each qzi is a free-form distribution. So as long as it's a distribution, it's fine. It's a distribution, and but they are factorized. So basically, this assumption implies that in my approximate posterior, this z1, z2 to zm are independent of each other. This is obviously not true. In many cases, it's obviously not true. But usually, people do this and find it's working well. So now let's look at given this approximate posterior family, how can we conduct the updates? Like how can we find out optimal approximate posterior in this form? Right? So to do that, we need to maximize the variational Probabilistic lower bound. Right? So this is an expectation, which is an integral, right? Integral the approximate posterior Q of Z with a log fraction, which is dividing the joint probability over the by the approximate posterior. Easy, right? So now we know we have chosen this factorized form. So we replace Q of Z by this product, and also the denominator here by this product, right? And how can we solve this optimization problem? So here we choose an alternative optimization, alternative updating scheme. Namely, like every time I just update one posterior, given all the other approximate posteriors are fixed. So suppose like I have like QZ1, QZ2, and QZ3, right? This forms their product forms your approximate posterior. So I'm gonna like each time I first fix QZ2 and QZ3 and update QZ1, right? And then I fix QZ1, and QZ3 up to QZ2. And then I fix QZ1 and QZ2 up to QZ3. I just do this cycle. So now let's look at like if I do this cycling or alternative update, how can we update each Q of ZG, right? This Q of ZG is a particular approximate posterior for ZG. Right? So if you write down the model evidence in terms of QZG, remember in this case, all the other QZIs are considered as a constant. Right? So you do not need to care about their terms only containing those terms, right? Only containing this QZIs. Right? So from the original model evidence rule of thumb, we can write this log fractional as log joint probability subtracted by this log posterior, right? And we can take a look at the first term. So the first term is integral for this part. So if you move Q of Zj outside this product, and the remaining part will be the product of the posterior for the other than variables, other than Zg, right? And then times this law of joint probability, and integral over Zg and all other Zi, right? So this part is essentially an expectation term. An expectation term of the law of joint probability under Q of Z not G. So Q of Z not G is defined to be the product of approximate posterior other than QZG. That's it. Does it make sense?
So then is that expectation also a product? Or are you just...
So this part is indeed a product. Right? So this product also represents an approximate distribution, right? Approximate posterior over like Z1 to Zj minus 1, Zg plus 1 to Zg, right? So just the approximate posterior excluding Zg. Of course, they still have a product, right? Because they are independent. They're joint posteriors, they're product. What we view it as like expectation of this log P of x and z under Q of z not G. Because outside we have to do the expectation over Q of zg as well. Right? Does it make sense? So let me give you detailed examples. So suppose I just have three random variables QZ1, Z2, Z3, right? So suppose I want to update QZ1. So in the first term, I can write it as QZ1, then QZ2, QZ3. And logarithm of P x Z1, Z2, Z3, and DZ1, DZ2, DZ3, right? Now, let's just merge this integral together. So I'm gonna like switch Z1 to Z3, so Z3 we first do the dz3 and then outside we do dz1. So this inner integration is an expectation on the qz2, qz3 of this law of joint probability. Right? Does it make sense? That's how we view it. And remember, this is essentially a random variable. Why? Yeah, we have a CG. So we do the integration, right? We do the expectation, we do the integration over z1, z2 to zg minus 1, zg plus 1 to zn, right? We have still one random variable left, which is zg, right? So this part is still a random variable, which is a function of zg. Does it make sense? Right? So you can write it as a function of zg. Then outside you need to do an expectation of this z function of zg with respect to qzg, right? Everyone is comfortable? Okay. Let us look at the second part. The second part is to integral. So remember, when we do the log fractional, we can write it as a log joint probability subtracted by log product of this posteriors, right? And the second part will be integral for this. So remember, we only care about q of zg. So that means like logarithm of qz1, z2 to zg minus 1, and those terms irrelevant to qzg can be thrown out, right? We only need to preserve qzg in this product. So log product is some summation of each term in the product, right? So that being said, the second term we only need to care about qz times logarithm qzg. Right? So all the other terms, like which multiply with qzg, you can just throw out because we do not care about them. They are constant. And now you do the integration with q of z. Remember, z is partitioned as z1 to zm, right? So for all the other variables other than zg, they are just integrating out. So we have a qzj, qzbg, dz, right? This is your q of z. They are factorized. Remember, and q of zg is here. You just multiply the approximate posterior other than zg, right? So when you do the integral over the entire z, remember q of z bj is not associated with this log term. You just move it off, right? And do the integration is simply 1. So the remaining part is simply the expectation of log qzg. This integral, namely the integral of qzg log qzg. Right? Is everyone comfortable? Yeah, I just give you the idea. If you like, still feel like uncomfortable and unclear about those details, I'll recommend you to derive it again. But this high-level idea, everybody should be good on that. So now our objective function with respect to q of zg becomes this. This first term is integral of qzg is with this expectation. The second term is integration of QZG and log QZG. Right? And now to optimize this, we can derive that the optimal Q of ZG is proportional to an exponential to this expectation. Remember, this expectation is the expectation of the log drum probability with respect to QZ not G. Okay? And this essentially is a function of ZG, right? Then you take exponential to this function of ZG, you still end up with some probability function, right? And then you do the normalization. The normalization is pretty straightforward. Just integrate this function of ZG over ZG and divide this exponential term. That's it. Any questions so far? Yeah, I'm gonna show it right now. Other than that, any other questions in understanding these updates?
Why do we? I guess I don't understand where the exponential came from.
Yeah, that's released. How do you derive this?
Oh, okay.
Yeah. I mean, given this updates, it's straightforward, right? I can even if you do not know why it looks like this. Now you can write down your MATLAB program or your Python program to conduct this update, right? Now I want to show you how this is derived. And so the easiest way of doing this is use the functional derivative. If you consider Q of Zj is functional, so you can take derivative or function as well and set the functional derivative to be 0. You can directly derive this. I'm not going to show that. I use the most stupid method to show that. So let me copy the bound here. The directional lower bound in terms of Q of Zg is simply the expectation of Q of Zg, and then this expectation term under Q of Z mod G and log 1 probability of xz and EZG subtracted by Q of Zg logarithm Q of Zg EZG, right? And now the very first step is you share the same factor like Q of Zg. Why not you just merge them together? So you have Q of Zg and you have this expectation log 1 probability subtracted by log QZG and DZG, right? So this becomes like awkward because I put an expectation outside this logarithm, so I cannot use subtraction between logs, right? So to overcome this issue, I'm gonna take logarithm outside and then take exponential inside. So this term is still copied. And subtracted by log Q of Zg. Right? So now I can divide them together, right? So I can do this. So it's a log fractional is exp over QG. And of course, if we write the full term, also you have to integrate this QGG and EZG, right? So now what does this look like?
maximize that by maximizing the.
Yeah, if we like, they're familiar with the definition of QL divergence, Q and P, it is Q logarithm Q over P over dx, right? Q and P are both that function of x. So now if we just take the minus in front, right? If we take the minus in front, you actually have QZG in the numerator. And this exponential term, log, in the denominator. Okay. So it sounds very similar to a QL term, but unfortunately, this is not valid QL divergence. Why? Why?
Is that a constant? The distribution. Was within expectation operation. So that's basically a constant. So
Yeah, exactly, right? Because this is a valid distribution, but this is not distribution. This is just a function of ZG. Here, right? As we just mentioned, this is a function of ZG. So now, why not we like intentionally construct a distribution on that? How can I do that? We intentionally normalize it. And we can write the normalization constant, which is exponential, which is an integral of this exponential term, and e q dg logarithm p of xz, and this ezg, right? Remember, this is a function of zg, right? So just integrate over zg. So we define this constant t, and t is constant to zg. Remember, because we do the integral over zg. So now I can, in the denominator, I can divide this exponential term over this normalization constant, and then multiply normalization constant, right? And outside is ezg. And this is a log, so that means I can separate this t outside. So with that being said, we have like q of zg logarithm q of zg over this exponential term over t and zg, and you move t outside, which will be like minus q of zg log 1 over t zg, right? The same thing, if you merge log, you will end up with the same thing. So now, what's this? It's just constant. It has nothing to do with zg, right? Because t is constant, you just move log 1 over t outside, your integral is 1. So the term that really determines the bound value is this one, right? So what's this now? It's KL divergence, right? It's actually the minus KL divergence between your QZG and your exponential of this expectation on the QZ naught G over its constant, over its normalizer, right? So when we want to maximize this lower bound, it is equivalent for us to minimize this KL divergence, right? So KL divergence is will achieve 0 when QZJ is exactly equal to this the same as the normalized distribution, right? So this normalized distribution is essentially this. That's how we prove this. It's kind of tedious, but it is. I think it's good practice. You can try to construct such a objective and think of why we should update that in our frame. So now it's clear how we do this alternative update. Right? So this is an algorithmic framework. At the very beginning, we choose a factorized posterior form. So Q of Z is factorized over QZ1, Z2 to like QZN. But you need to first partition your random variables, right, into a set of sub-vectors, sub-variables. You have a question?
No.
Okay. in an extreme case, like you just factorize over individual elements.
Yeah, so obviously we have a lot of potential form for QZ. Why do we choose the factorized form? Because I think there will be other forms too.
Yeah, yes, of course you can. You have other forms, but you can consider like you either choose QZG to be like some Gaussian or whatever parametric family, right? Or you can choose I put some general factorization structures, but I do not restrict the form of QZG. So this is another kind of flexibility. That depends how you choose it. If you believe like QZ is a Gaussian distribution, you can do the same thing. You can do the optimization, right? But if you think I do not want some parametric form, I want this bound determines the parametric form, then I can put some factorization structure on that.
Does this factorized form forms better compared with the other parametric form?
There are some theorem associated with that. So basically, if you choose a mean field variational framework, so I can guarantee that your mean under a large number of instances will converge to the true posterior mean or true posterior marginal. Like if you choose to factorize over pairwise random variables, like partition them by 2 as one group, then under the large data limit, it will ensure that the expectation is converges to the expectation of the true posterior. That's some kind of benefit for mean field variational inference, but they won't like guarantee like second order movements or third order movements. But again, there's no right or wrong. You can choose whatever you want. Here, I just give you one common used example. So, and then in each iteration, I just cyclically update each posterior Q of ZG, right? So I fixed all the other QZIs, and then update Q of ZG to be proportional to the XP exponential of the expectation of log marginal probability under the posterior of all the other random variables. Then if you do this cyclic updates, you finish one iteration, and then do the next iteration, you end until, like, for example, each Q of ZG changes little, or you have already reached the maximum number of iterations. Any questions so far? Okay, so now let us look at some concrete examples. So I want to use mean field variations to estimate the basic linear regression model. So here's the regression model. So basically, in my Poire distribution of the big vector W, I'm going to first sample the precision or inverse variance derived alpha from some gamma distribution. And then, given alpha, I will sample W from a Gaussian distribution with mean being 0 and covariance being alpha inverse identity matrix. So alpha is precision parameter. And then, given W, I sample each data point from a Gaussian distribution. So the mean is the inner product between the bit vector and your feature vector, and the covariance or the precision is beta inverse. So is beta. So here we assume beta is constant, is normal. But actually, if you assume beta follows a gamma Poire, you can do the similar kind of updates as well. So, by the way, this product of likelihood can be written as one Gaussian term. You have done that before, right? Because this is just some individual Gaussian, right? You just multiply them together, you have like a big Gaussian with diagonal structure. So here, I just rewrite it here as a distribution over T. T is vector, consists of all the responses. So the mean will be the design matrix multiplied with W, right? And covariance will be beta inverse I. This is just a matrix representation of this product. So now we can write down the joint probability. Right? The joint probability of your response observed when variables t and the b vector w and the Fourier parameter alpha is the likelihood p of w multiplying with pw given alpha and p of alpha, right? So given the observed n responses t, right, our inference task is to compute the posterior distribution of the w and alpha given t. This is our task. So obviously, you won't be able to compute the exact posterior. So we'll seek for the variational inference. So we'll introduce a factorized approximation in that the posterior w and alpha, we assume it is factorized of the posterior qw, posterior of w and posterior of alpha. So we assume it is a product of q of w and q of alpha. So again, this essentially assumes the posterior distribution w and alpha are independent. Obviously, this is not true. This is not true. This is just an approximation. So then we do alternative updating. Right? We can first update q of alpha. Q of alpha is updated with being proportional to exponential of the expectation of the law of joint probability under q of w. This is just the rules we just mentioned, right? So just take logarithm of the joint probability, then takes expectation under the approximate posterior of all the other variables. Here is q of w. Then you take exponential again and normalize it. So now let's look at what does this look like. What does this exponential term mean? Right? So we need to write down the log joint probability, which according to our definition, you can written as a product of the product of w, product of alpha, product of w, product of t, and the likelihood of t being w, right? So this is actually the log summation p alpha given p0 and p0 plus logarithm pw given alpha. Logarithm pt being w, right? But here we only care about the posterior alpha, right? So any term that does not relate to alpha, we can throw it out because it's constant for alpha. So actually we do not need to compute this log term. So we only need to look at the log prior of the alpha, which is log gamma, and the log prior of w given alpha, right? So the gamma distribution will be something like this. Alpha to the power a0 minus 1 and exponential to b0 alpha. So I just recited nothing special. And something constant. But this constant does not contain alpha, so I do not write it down. So if you take a logarithm, it becomes a b0 minus 1 log alpha minus b0 alpha. And then let us look at the logarithm of this prior of w given alpha, right? So this is a law of Gaussian, right? So law of Gaussian, it becomes like, if you write down the law of joint probability, which is 2 pi alpha inverse I determinate to the power of minus half, right? And then exponential to minus half alpha w transpose w. I just recite the formula. Right? If we take logarithm and just pick up alpha, be careful, alpha here multiply with an identity matrix, right? So if you want to compute the determinant, you have to take the power of the rank of the determinant. So suppose your w is like d-dimensional, so I have to take alpha inverse to the power of d. It's not directly factor of alpha. That's wrong. So if you look at the log determinant and extract the terms that relate to alpha only, it will be like alpha to the power of minus b and to the power of minus half. So it will simply be to the power of half b. Minus minus becomes a positive, and half power of d multiplying half, and then subtracted by log exponential just cancels, so just W transpose W alpha. And log alpha to the power of half d, you can just move the exponent in front of the log, right? So it's just half d log alpha. Right? It's just a mechanical computation. I just write every step to ensure like everyone feels this is really simple, nothing special. So you can do this. Right? And then we can merge terms. So we have like A0. Now this term works together, right? You have A0 plus half d minus 1 log alpha, and subtracted by E0 plus half W transpose W. Right? And this is just law of probability. Then you have to do the expectation on the Q of W, right? So the term only that relates to W is this W transpose W, right? So you can simply take expectation here. It's just B W transpose W. So now we take exponential here. What's this? What's this distribution? This is still a gamma distribution. Right? If you look at the general form of gamma distribution, right? For a general form of gamma distribution, say x, a, and b, it's just proportional to a to the power of, x to the power of e minus 1 exponential minus br, right? So if you take logarithm, you have a minus 1 logarithm x minus br, right? So now you just match the form. So you know, okay, your new distribution have like an to be a0 plus half d, right? And bn to be b0 plus this half expectation of W transpose W. That's your new parameters for your approximate posterior alpha. That's Q alpha. And the expectation term that is expectation W transpose W is easy to compute from the Gaussian distribution because QW because once you have a QW in hand, you can immediately compute expectation, right? So now this is how we update Q of alpha given Q of W fixed. And next we can update Q of W given Q of alpha fixed. The same thing. Right? So again, let me simply copy it. So I do not need to write down again and again. So again, we first take a logarithm of the drawn probability, right? So because right now we want to update Q of W, so any term irrelevant to W can be thrown out. Right? So basically, the log prior of alpha can be thrown out because it does not contain W, right? So the only term you need to take a look at is logarithm P of W given alpha plus logarithm of P of T given W, right? Log likelihood. This one is a Gaussian, and this one is a Gaussian. So if you take a logarithm and just extract terms related to W, just the two quadratic terms, right? 1.5 alpha W transpose W minus half beta and T minus by W transpose T minus by W, right? So this comes from the one big Gaussian distribution I just mentioned. If you extract it, it's just like this. So now you can tell me if I take the expectation. If I take expectation, I want you to take the expectation of alpha here, right? And then I do the exponential, and then I normalize what's the distribution for this. An idea? What's the distribution for this? Can you guess?
Still normal.
Yeah, still normal. Intuition is right. Remember, we have introduced completing the square trick, right? So whatever distribution, like if you want to test whether it is a Gaussian distribution or not, you just need to test whether if you take a logarithm, it has like quadratic term and first order term. If you have something like half like W transpose A W plus W transpose B, it must be a Gaussian, right? Because if you expand your Gaussian term, you take exponential, you take a logarithm, you cancel the exponential, the quadratic term, if you expand them, it's just this form, right? So now you can merge the terms here to match this form. You will find out your mean and covariance, right? So I'm not going to show the details because everybody has done this before. We have used completing square tricks to show how to derive a condition Gaussian distribution, right? How to show that the marginal distribution for any multivariate Gaussian distribution is still Gaussian. The key trick is this completion square completion trick. So here we use the same trick. That's why we emphasized before, right? You have to practice this because it's very common. So now, given alpha, I have a way to update Q of W, right? Both updating are kind of analytical. And then during the updating, we need to compute the expectation term, which we call moments. So to update the Q of W, you have to calculate the expectation of the alpha according to the curve, the approximate posterior form of Q of alpha, which is gamma. So the expectation is just n divided by bn. And because Q of W is Gaussian, so the expectation of W transpose is just the covariance plus outer product of the mean vector, right? And then you can do this alternative update until convergence or the maximum number of iterations achieved. And finally, you can find your approximate posterior distribution, right? Again, with this approximate posterior distribution, you can compute the predicted distribution. So predicted distribution is the likelihood multiplying with the posterior distribution of the W and integrate all the W so that you can get the distribution of your test response given the training data. So this likelihood, so given any test input, the likelihood P of t given x W is a Gaussian, right? And the posterior approximation is a Gaussian. So we multiply them together, you still end up with Gaussian. So it's pretty straightforward to compute. Right? So now, someone may ask, right? So I have this golden rule, as we mentioned before, right? So we every time I just fix all the other posterior distributions, update the current posterior distribution proportional to exponential to the expectation of this log John probability, right? So naturally, we want to ask, are there, like in all kinds of situations, we always end up with analytical form? The answer is no. it cannot guarantee like for arbitrary factorization, arbitrary drawn probability, this kind of update will give you an analytical form of the posterior. So in that case, as you just mentioned, we need to specify some parametric form and do the optimization rather than this alternative update. But here I want to give you a general case that you can do this analytical form always. That is under the conjugate part. So you can see the conjugate part is really useful, but it's kind of oversimplified. So suppose your random variables. These random variables consist of two parts. One is eta, and the other is z. And you're going to first sample eta from some bar, and then given eta, you sample z, and given z, you sample x. So here we just assume like the prior for eta is conjugate to the likelihood of z and x, and the likelihood of z and x is exponential family. So we previously, as we previously mentioned, right, like we have for any like exponential family distribution, we have this form for the conjugate part, right? So if you follow this form, and then if you want to compute the posterior distribution of eta and z following the mean field approximation family, so you factorize over q of eta and q of z, then you do the alternative update, it will guarantee it to be analytical. And in general, analytical form is Q. Just Q. So I won't show you details because it's quite mechanical. You can verify this updates on themselves. Any questions so far?
So just going back to the linear regression example. So yeah, we have our estimation for the joint probability by multiplying Q of W and Q of alpha.
Yeah.
So we get a distribution for Q of W, we get a distribution for Q of alpha. Then the last step would be to get it in the form of or essentially to run optimization on it. Like,
yeah, when you do the alternative update of Q of W and Q of alpha, you're actually optimizing Q of W and Q of alpha. And after convergence, you end up with your optimal estimation of Q of W and Q of alpha. And the guarantee is that this product will be the closest to the true posterior, given its factorized form. So this is an optimization procedure.
oh, interesting. And that's what you mean by like analytical solution is
Yes.
that just is the optimal. Okay.
Yes.
Okay.
Yes. So basically, like if you want to optimize a function of two variables, right? Say fx1 and x2. The idea is that like I fix x2, then optimize x1, and I fix x1, optimize x2. I do it alternatively to convergence. And under bound conditions, it will converge to some local minimum or local maximum. The same idea. So actually, there is this updates essentially is to calculate the natural gradient of the model evidence lower bound set natural gradient to be 0. You will end up with the same update. I'm not gonna show the details about that. But just to show you like how you do this alternative optimal update.
Okay, and then that's why the exponential family is useful, because then we can combine the gamma distribution with the Gaussian distribution.
Yes.
Okay.
Yes.
Gotcha.
Yes. So this is a typical like we have a gamma bar, which is conjugate to the Gaussian likelihood, right? So you can say their alternative update is analytical. Nowadays, like if you want to join calculate posterior distribution, they won't be feasible. Any other question? Okay, great. So we have finished the global layers of interest topic. So let's continue on next Monday, we'll talk about local variation inference, which depends on the convex conjugate.
Yeah.